Chapter 5 Combinational Logic Design Practice. On this chapter, we describe about device, structure, and method to solve practical design problems, which maybe have dozens or thousands of input and output. So, in practical, for the complex circuit or system, okay, we usually uh, design with main circuit and sub-circuit. Okay. For example, they often use sub-circuit such as decoder, encoder, multiplexer, adder, comparator. Okay. 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 For this page, just try something about documentation standard. Okay. When you do some design project, maybe you must communicate with your friend or your partner. So it's very important, okay, to do document with the standard in order to you can communicate, okay, and work with another one in your team. Okay. So in the type of document that I often use, the first one is specification. Okay, we describe what the circuit or the system is supposed to do, what is the input and what is the output of your system, and what the function, okay, that you want to perform. Block diagram, okay, schematic, time diagram, and circuit description, okay, something like this. Okay, let's see. For block diagram, okay, block diagram, for example, this one, okay, we showed the input and output, okay, and functional module like this: control module, register module, okay, and so on, and show you the internal data part, okay, to show the flow of data from this module to this module, okay, and so on, and some control signal. For example, this device is controlled by this signal, this device is controlled by this signal, and so on. For block diagram, we just write and write the name to show some function of that module. We will not write so detailed like this, okay, not like what kind of IC that use the circuit to implement the function. For the we don't, okay, write some detail like this, okay. Okay. For the gate symbol, okay, as you know, okay, the basic logic gate and or buffer. And for this one, there are two input, right? Two input AND gate. But if you write, for example, 10 or more input, if you write something like this, for this one, two input AND gate, and you want to write about 10 input AND gate, you write something like this. What happened? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oh, it's very big, right? It's so big size. So in practical, we extend, okay, input, okay, for so many input, okay, terminal of the logic gate. For OR gate also, okay, extend, and then we write something like this. And inversion bubble, or it work as function of invert. For example, if I add inverter, okay, at the output of AND gate, then it become NAND gate, right? But usually we just write this circle. It's called inversion bubble, okay, to show the invert function of this point. NOR and inverter also. before describe the detail, consider these two words: active high and active low. In practical, you we often give the name of signal or variable in some expression. To name the signal, usually the name should indicate its duty. For example, go, pause. This is some kind of control signal already or error. It's conditional signal or input bus. It's data signal. The name to show some duty or have some meaning. And for example, for some control signal and maybe also conditional or data signal. Normally we have two kinds about the active level. The first one is active high. Active high, namely, for example, this one, clear. If we want to clear data, if the signal of clear is 1, then the circuit clear all data. Some kind of this is called active high. It will active when the value is high. And for active low, something like this, clear. The circuit will clear the value when the value of this is low or 0. So, to name and to show that this signal is active high or active low, we can name with so many style. Anyway, the often used is this one, clear. For example, clear for active high. Right, just simple name. But for active low, we will add bar over the name or underscore L, which show that this is an active low. For example, this one, for the symbol logic gate, this one is active high. But if I add circle around here, that means this one is active low, or this one active low. For example, this enable is some control signal. If enable active, the circuit will operate normally. For example, this one, the circuit will active just when logic 1 is applied to this enable input. So this one is active high. But for this circuit, have this inversion bubble, that means this one is active low. So if you want the circuit operate normally, you must apply 0 at here. So so for this one, consider it is very, very important. For AND, for AND function, normally the output will be 1 when both input is 1, right? But from now, you must be able to consider the AND function as the output will be active or assert when both input active. Note, I just changed the word logic 1 to active, right? Just change 1 to active. For this one, Output have no inversion bubble, input also have no inversion bubble. That means output is active high. Okay? This input also active high. And now, okay, let's consider this one. Okay, this one first. You know that it's NAND gate, right? But now we consider the body. The main structure is AND, right? It's AND function. The difference just the output is active flow. Okay, it's active flow output. So again, because of AND body structure, so we can say that the output will be active. Okay, if and only if both input active. So if I apply 1, 1, okay, it's active high, right? So that means this input active, this input active. So output should be active. But output now is active low. That means when input active, the output should be 0. Okay. So apply 1, 1 active both, output active. Active flow, so output is 0. How about this one? This one, okay, the main body again is AND. That means output will be active when both input active. So if I apply, for example, 0, 0, so it's active low, right? So when apply 0, 0, so this input active, the input active, then output active. And because there is no inversion bubble at the output, this one is active high. That means when this output active, the value will be high. Okay? And now let's consider if I apply 1 at here, 0 at here. How about the output? So this one active low, right? But you apply 1 which is high. So this input not active. And you apply 0 at this input active low. So this one active. And because of AND structure, so one input not active, then output is not active. And because output is active high, okay, no inversion bubble, so when output not active, that means the value of the output is 0. Okay, so when you apply 1, so output is 0. How about this one? When I apply 1 at here, 0 at here, this one not active, this one active, so output not active. And because output is active low, so when it's not active, the value is 1. That's all. So you need not to know the name. Actually, you need not to know the name. Okay, you just know the main body is AND or. So after that, we should consider is active or not. That's all. Okay. For example, this one. For this one, if I apply 1 at here, 0 at here. Okay. The main body is OR. Okay. For OR, output will be active if one of input is active, right? This one is not active, but this input active, okay, because it's active low and you apply 0 at here. So output will active, and because output is 0, right? Then when output active, the value is 0. Okay, so we can analyze very easy by using this method. So how about this one? For buffer, when input active, output will be active. So for this one, when you apply 1, oh, it's active high. When you apply 1, so it's active. Output also active, and output is active low. That means when it's active, the value is 0. Okay. What about this one? When you apply 1 at here, but it's active low, right? So it's not active. Output also not active. And because output is active high, when it's not active, so the value is 0. That's all. Something like this. It's very easy, right? You just know the main, okay, body or main structure of logic gate. After that, you just consider the input active high or active low. Okay, that's all. And based on this, okay, uh, active high and active low. Okay, let's consider this circuit. If I want to know the output when I apply the value 1, 1, 1. Okay. So normally for the simple uh, analysis method, we may consider is 1 at here, right? And SEL select signal is 1, so output is 0 at here, right? Because this is inverter. And 1 and 1 is 1 and then invert with 0 at here, right? 1 and 0 is 0 and invert then become 1 at here. 0 and 1 is 0 and invert then is 1 at here. Something like this. Anyway, so from this one, actually we can convert. We can convert. Okay, maybe you. Okay, do you remember? For this one, I can move this inversion bubble. Okay, from output side to the input side. Then when the bubble pass through the body, okay, it will change, okay, from AND to OR, okay, then it becomes this. And now note this bubble and this bubble, right? And this output is active low, so connect to active low input of this logic gate. And for inverter also, okay, we change, okay, to this one. Okay. So now note now active high signal connect to active high signal. Active low signal connect to active low signal. Some kind of this is called bubble to bubble. Okay. So when you analyze the circuit, it's very easy because okay, you connect the same active level. Okay. This output active high connect to this active high input. Okay, and this active low output connect to active low input. So if I apply, for example, 1, 1, 1, so what happened? It is active high, right? So it's active at here, right? Active at here, but this one not active, and active at here. When this input active, output also active because the main structure is buffer, right? When both input active, so output active also. Okay, this one also active, and when this one active, so output also active, and because output is active, right, the value is then 1. Finish. Okay, it's more comfortable, okay, if you use some kind of this bubble to bubble logic design. Okay. And now let's consider the basic input when you implement the circuit. The first one is switch. Okay. Switch. For example, this one is switch, right? And this one is resistor. And connect to ground, connect to VCC, okay, positive 5 volt. So let's consider if the switch is released, okay, it's open circuit, right? So if this point connect to nothing, so how about this point potential? No current, right? No current. That means the voltage across this resistor is 0 volt. That means this point and this point is the same, right? Voltage difference is 0. That means this point and this point have the same potential. This point is ground. Ground means it's 0 volt, right? So this point then 0 volt also. So and what happens if I press this switch? Okay, when the contact of the switch, okay, contact this point and this point. So now this point then is connected to 5 volt directly. So then this point then become 5. 4. So this kind of switch configuration is called active high, because when you do the action, when you press the switch, it makes this point become high. And how about this one? For this one, okay, if the switch is not pressed, so there is no current, right? There is no current. That means the current pass through this resistor also is zero, right? When current is zero, that means the voltage across this resistor will be 0 volt. So voltage difference 0 volt, that means this point and this point are the same potential. So this point is 5 volt, that means this point must be 5 also. Okay, 5. Okay, when this switch is open circuit, and when you press the switch and then become short circuit, so it's connected to ground directly, right? So this point then become 0 volt. So this kind of switch configuration is called active low. Active low, because this point will be low when this switch, okay, is pressed. Okay, when you press this switch, make this point become low or zero. So it's called active low. And for the output, the basic element is LED. Okay, LED. For LED, actually it is one kind of diode. Okay, when the current, okay, flow through this LED, okay, will be turned on, and then will be emit, okay, some light. It may be red or green or yellow. Okay, it's on the type of LED. Anyway, for this one, if I connect to this one, right? Oh, one thing that you should know about diode or LED, the current can flow just only one direction, from this terminal, okay, to this terminal. This terminal normally is called anode. Anode, and this one is called cathode. Okay, anode, cathode. So for this one, the current will flow when you apply 5 volt, right? Because ground at this point 0 volt. Okay, the current flow to this one, then the light turn on. So you apply 5, apply logic high to make this output LED turn on. So it's called active high. Okay, but how about this one? I connect 5 at here, right? If you want to make this LED turn on, you should apply what? You should apply 0 volt, right? Because if you apply 5, okay, same potential, there is no current, right? But if you apply 0, when you apply 0 at here, so the current will flow from 5 to 0, and then make this LED turn on. So it's called what? The LED will turn on when you apply 0 volt, right, at here. So it's active low. Okay, output signal. On this one, did you solve something about this? If I connect input from this to ready signal, connect input from this with to request signal, and connect go to this LED. Okay, if I want to implement circuit with function that this LED that connect to go, okay, will be on when the switch ready and request, okay, are pressed, okay, both at the same time. So based on this one, from this connection, it should be AND function, right? AND function. Okay, ready and request must active at the same time to make this output go active or make the LED turn on. Anyway, for this one is active high, so you do nothing, right? But ready, okay, this next is active low, so you need to add inversion bubble at here. And how about LED? This LED also active low, so you must, okay, just add this inversion bubble, so you can complete the circuit, okay, for this condition. So it's very easy, right? If you understand the concept of active high and active low, so you can apply it very easy. And for the when you draw something like layout, okay, of the circuit diagram or schematic, usually, okay, we write the logic gate, okay, in this orientation, okay. Input is in left side and output is in the right. And for something like line, okay, or wire, about its connection, okay, the line is just causing all it connect together. How do you know? Okay. You should know some standard, okay. If it cross together, something like this, or sometimes you see something like this, just cross together. But if it connect together, normally it should have black junction, okay, black circle at here, or maybe something like this, okay. Stop at here and then stop at here. And for this one, okay, when you add, okay, circle at here, so it can show that it's connect together. But for machine it's not allowed, so we want to connect. Normally just like this one, okay. And for the schematic or the circuit diagram, if it cannot fit in the single page, so you should broken up into individual page in and there are two ways, okay. The first one is draw the layout with this flat schematic structure. For this one, every page, okay, okay, we have the same detail, okay, the same level of the detail. For example, for this one, this output connect to this output, okay. For this this page, you write the circuit in logic gate level, right? This one also, okay, you write in logic gate level. It's the same level. This kind, okay, of structure is called flat, okay. And something like map, right? Like map. When this maybe this road, okay, and then from this page to this page, something like this. It's called flat schematic structure. Another one is hierarchical schematic structure. Okay, now the detail of this page and detail of this page are different. For example, the first page may be something like the main uh, functional box, okay, and for the detail of each blocks, you may write in another page, okay, to show the detail. Okay, this kind of schematic structure is called hierarchy, right? And bus. What is bus? Okay, consider this one. If the signal, this one address 15, connect this point to this point, and address 14 signal, the wire connect to this point. So if you write something like this, so there are many line or many wire display on the paper, so it's not so convenient for the human to look. So that for that reason, so normally we do a collection of 2 or more signal line together, and after that when you want to connect, for example, this address this signal to this one, you just split each bit from this bus. That's all. Very easy. And this will show you something like the microprocessor, which maybe have some address address data data have 8 bit. There are data 7, right? Data 6, and so on until data 0. So there are 8 bit for data signal. Then we write with the symbol. So it's quite easy for you, right? And to complete the schematic diagram, usually we will indicate the IC type. This one IC type 74HCT00. This is just for NAND gate. Or this one 7404. This one is inverter. You should indicate. And for reference designator show you that this logic gate is from IC name U1, and for one IC normally there are 4 U1. All of these are in the same IC, and this one is the second one, U2. So the reference to show the name of IC that user maybe set the name by himself. The circuit diagram also to show the pin number to make it very convenient if you make or implement the circuit follow this schematic. And for timing diagram is used to explain timing relation among the signal within the system. For example, when input go from 0 to high, go is active high, right? So when go active, actually go is something like enable. So when go active, it make ready change from low to high. So when ready, active, and go active, then maybe this circuit do something and make the data change. To write down to show that the change is from this chain. So we can write that this ready. This ready it change. Okay, when go change. So we draw some arrow, right, to show that the change is caused by this input change. So it then is called TRD1. Okay, ready. Okay, ready signal, and the change, okay, at the output data, okay, also due to the change of input go. So we okay, show this is by this arrow, okay, to show that this is the this chain, okay, make this output chain, and some chain, okay, sometimes for example this go chain, sometimes ready signal chain fast, sometimes the signal chain slow. Okay, so so then now we write uh, the worst case. So I mean it is fastest, okay, and this one is slowest. So what happened if this go change and ready maybe change at this timing or at this time, but you don't know, right, in practical. So to make sure that the ready signal, okay, already set, so you must wait, okay, you must wait with this delay, okay, propagation delay, the maximum propagation delay. Okay, so you can be sure that, okay, at this point of time after this maximum of propagation delay, so you can be sure that the ready signal is 1. Okay, but at this point it is not sure, it may be low and then become 1 at here for this one also. Okay, and the fastest change at this point of time or minimum, right, and the slow rate, okay, or maximum propagation delay at this point. So normally we use worst case, okay, delay, okay, to analysis and design. Okay. And how about this? The timing diagram. Sometimes, okay, we write in this style, namely this right underscore L. This one is active low signal, right? So when this right signal, okay, become low, then it's active, right? So maybe it will read the data from data in. That means this period, okay, data input must be stable. Namely, data input may be 1, okay, maybe 1, or maybe 0, right? So you just write with this style to show that it's constant. It's constant logic level, maybe high or maybe low. And after that when it change to high, so it may be change to some value, and okay, when this input change to the right is right, so this data is read, right, and then you show to the output, you must wait with some propagation delay, and then uh, the output of data out, then you will change to the new value from data in. Okay, that's all. Okay, and note for this one, This one is change. Maybe it change from low to high at this point of time, or change low to high at this point of time. And some signal is change from high to low, okay, at this point of time, or this one, right? Change from high to low. But in practical, you don't know, right? When now you change. So in case so we write, okay, to cover minimal case of fastest and the slowest case, okay, of the operation delay. And this example, clear is active high, right? No underscore L, okay. Count also active high, and this is step, okay, value is 8-bit, okay. So if at the beginning the value of step is ff means 1 1 1 1 1 1 1 1, okay. And when clear active, okay, 1 change to 0. Clear means make, okay, the value to be 0. And after that, when count active, okay, the value of step, okay, will increase, right, with 1, okay, value of 1. When count active again, so the value will be count up, right, from 1 to 2, okay. When signal is active again, so the value of step then change from 2 to 3, okay. So note, okay. For this simple, you write something in this. That means it may be some change, okay. And this one also, maybe something change from high to low or high or low to high. Okay, and now, okay, you study the first often used device in practical. Okay, it's decoder. Okay, decoder have got multiple input and multiple output. Okay, decoder normally we use to convert, okay, code input. Coded input mean something that that's so hard, okay, for human, okay, to understand, to understand the meaning, okay. So it convert, okay, coded input to into coded output with easier to understand. For example, in binary system, 1101. Do you know value in decimal? Someone knows, someone not, right? So this one is what? It's 13 maybe. So to make, okay, it easy for the human, okay, for example, so sometimes we may use decoder to convert binary input to some one out of output. For example, like this. For this one, to show you some example. There are two input, so output should be 4, right? And this circuit have enable input. That mean when input is when enable input is 0, enable is not active, right? It's active high, no inversion bubble at here. So when enable is 0, circuit not active. So output y2, y3, y1, y0, all of this will be 0, okay, 0. And when enable is 0, okay, the value of I0 and I1, okay, not affected. So we can write with XX. XX mean it can be 0 or 1, okay. Anyway, the value of this I1 and I0, okay, don't affect, okay, the value of the output when enable is 0. However, if enable is 1, if enable is 1, the output will be based on the value of 1, I1 and I0. For example, when enable active is 1, right? When you apply 0, 0 at input I1, I0, so output Y0 will be active. And when you apply what? 0, 1, right? 0, 1. 0, 1 mean 1, right? So Y1 active, okay? And when you apply 1, 0, okay? 1, 0 at here, 1, 0 is 2, right? So Y2 active. And another output is not active. And when I0, I1 is 1, 1, it means 3, right? Y3, Y2, Y1, Y0, okay? Will be Y3 will be 1, right? Y2, Y1, Y0 will be 0, okay? The output will be active, just only 1 bit. That corresponding to the input value. Okay? This kind of output is called 1 out of and number of bit, right? That means it will be 1, just only 1 bit, okay? From maybe m bit. Okay, now now you understand, okay, the function of decoder. And now let you decide. Can you decide the decoder? Okay, based on this table. Okay, this circuit. There are 1, 2, 1, 2, I1, ISO, and enable as control. Okay, input. So if I want to know the equation for Y3, okay, maybe I just consider the logic 1 output, right, of Y3. So it's 1 when what? When I2, when En, I1, I0 is 1, 1, right? So you can write Y3 as what? En and I1 and I0, right? Like write midterm, okay, for a general function. And how about this one? 1. Right? It will be 1 when what? When input En, I1, I0 is 1, 1, 0. So you can write the expression, okay, for Y2. Y2 equal to En and I1 and I0 prime, right? Like you write midterm for this Y2 function. And for Y1 also, okay, similar. Y1 will be active when enable is 1, I1 is 0, I0 is 1. Okay, so the equation for Y1 then is En and I1 and I0. For Y0 also is 1 when what? When enable is 1, right? I1, I0 is 0, 0. So for this one, you can write as En and I1 and I0. Okay, that's all. When you obtain the equation, okay, for all output, so now you can implement, right, the circuit, maybe by writing the circuit diagram, and then you bring, okay, the logic gate, okay, connect together. After that, you may test the circuit, okay, by apply input signal and observe, right, the output signal. For example, if you apply enable is 1, I1, I0 is 0 0 0 0. So what happened? So 0 0, then is one y0 will be active, okay, and y1 y2 y3 are not active. So there will be only one bit, so it's called 1 out of m, something like this. So okay, when you get the circuit, okay, after you implement, you may apply, okay, some value. Normally we apply, okay, all possible value to check the output. In this case, I apply 0, right? At enable is 0 at here, and then when enable is 1, I just apply 0 1 at here, and what? Oh, sorry. So 0 at here, and then 0 1 at here, 1 0 at here, and then 1 1. Okay. And to show some example. And then this page just show you, okay, for gray code, okay, do you remember about gray code? When you plan the disk, right, and you maybe have some sensor, okay, to detect the color, to detect the light, that it is transparent or not, okay. So for this one, okay, your output may be in gray code, but you can consider it's similar to the binary code. So you can use decoder, okay, to decode this gray code to the output the active only one bit. For example, if enable is 1, right, and input is 0 0 0, okay, y 0, okay, should be active, right? Okay, y 0, okay, active. So you can define, right, the angle or the position of the disk, okay. For another output also, okay, you can define, okay, follow the practical position of the disk. And the most important thing that you know, that you can use binary decoder, okay, to create or implement any logical function. Why? Okay, let's observe something like this. Okay, when enable is 1, keep enable is 1, so the output y0 will be active or will be 1 when input is 0 0 0, right? That means you can write the expression as I2 prime, I1 prime, I0 prime, okay, and if I apply 0 0 1, right, y1 should be active, so you can write the expression for y1 as I2 prime, I1 prime, and I0, right, 0 0 1. Okay. For another output also, okay, you can write the expression for each output, and so you can note, okay, that the expression is something like minterm, and you have know already that any function, okay, can write in the expression of canonical form, okay, or sum of minterm. That means, for example, for this one, this function, if I want to implement function f1, okay, maybe I apply one enable and connect input A, B, C at here, right? So output F1 will be 1 when what? When input is 0, 0, 1. 0, 0, 1, the corresponding output is Y1, right? Maybe when you apply 0 0 1, okay, at A B C, then Y1 is active, and when you apply 0 1 0 0 1 0, okay, Y2 active, and when you apply 1 0 0 1 0 0 Y4 active, and when you apply 1 1 1 1 1 1 Y7 active. Okay, so you just right bring this four term, okay, all together. F1 function, okay, it's like you combine, okay, or sum of this min term. Okay, how about F2? For F2 also you connect A, B, C, and I2, I1, I0, and apply enable is 1. So when you apply 0 1 1, right, Y3 active, 1 0 1 Y5 active, 1 1 0 Y6 active, 1 1 1 Y7 active, and then you all this term together, okay, to complete third function. Follow that. And how about F3? For F3, if you do the same method, one at here, A, B, C at here, you must hold all of almost, right? Almost output Y7, Y6, Y5, Y4, Y3, Y2, and Y1. Okay, a lot. So it is not so good. And how about if I consider logic 0 output? Okay, enable is 1, A, B, C. Okay, now function F will be F3, okay, will be 0 when input is 0 0 0, right? So you can write F3 as what? As A or B or C, right? Okay, A or B or C, okay, 0. Okay, just only one case, or max term. Anyway, the output of decoder we write in product term, right? Not sum term. So what should you do? Maybe you must invert, right? Invert, put invert, okay? Invert and invert. If you keep this invert and invert this term, then it become what? Then it become A prime and B prime and C prime, right? And then invert. This one is what? Is Y0, right? And then invert. Okay, that's all. What is F3? And the last one, F4. How about F4? F4 0 0 at here, right? So you can consider these two cases that make function to be 0 by what? By write a canonical product, right? So F4 1 at here, A, B, C at here. F4 is 0, okay, when A, B, C is 1 1 0. So you can write as A prime plus B prime plus C, right? And what? For this one is A prime plus B prime plus C prime. Okay, and then when you use them again, right? So this one then is become A and B and C prime, right? Or what? Or A and B and C. Okay, this term. So this one and the corresponding output is what? Y7, right? right? Oh, sorry. Y private here. This private here. Y6, right? And this term is Y7. So you add these two terms and then invert. You will get function f4. Okay. Okay, that's all for today.